Welcome to day 29 of AP Calculus BC. We're still in the midst of our series convergence tests, though we are almost at the end. You can see the light at the end of the tunnel. This is day 29 out of 31 lessons, so we've got today and two more, nothing too bad. Today we're going to focus on the limit comparison test, which is really a better form of the direct comparison test. There's very little that the direct comparison test can't do that the limit or the direct comparison test can do that the limit comparison test can't do faster. So if you didn't like the direct comparison last class, then you've got a much easier option this time, and if you did like it, well, you just get to learn another test. So opener-wise, we have the graph of f of x over here, g of x over here, and your goal is, of course, to perform these wonderful evaluations on the right. So please go ahead and pause me, try those 5 evaluations. They should not be super terrible, and then we'll talk about our lesson. Okay, hopefully you went through here. I can run through these very quickly. There's nothing too bad. F of 1 times g of 1 looks to me like 0 times negative 1, which is 0. We have g of 2 divided by f of 2, which no need to simplify there. F of 2 divided by g of 2, I can do that one, no problem. F of g of 1, so let's see, we need to find g of 1 first. It's negative 1, and then f of negative 1 is negative 3. And then last but not least, f of 1 is this guy, which is 0, and g of 0 is 2. Awesome. Nothing too terrible there. The reason that we did this opener is so that we could just practice having two different functions and relating them together. So let's go ahead and jump onto the limit comparison test, where that's exactly what we're going to do. So the limit comparison test is, in my mind, way more useful than the direct comparison test. I very rarely, if even ever, I come across a problem where I won't use the limit comparison test. Instead, I say the direct comparison test will be way better, because that just really doesn't happen. It is similar to the direct comparison test. You still need to choose a series to compare to the given series where you know that series' end behavior. However, instead of determining which series bounds the other, remember when we did the fractions, which fraction is bigger, which fraction is smaller, all the limit comparison test does is it basically finds the largest term in each series. Right? So it goes out to infinity and says, at infinity, here's the value of this series, or sequence in this case, and then, yeah, I probably should be saying sequence here instead of series, it says at infinity is this value of the sequence close enough, in air quotes, see I did it down here, close enough to the value of the other one. If they are close enough, then you can actually divide them and get a finite answer. However, if they are too far apart from each other, then they have different end behavior. Essentially, one function dominates the other, and then that's going to end up being something else, right? And remember when we did function dominance with limits way long ago, we talked about one function dominates the other. We talked about the order of dominance. We're pretty much doing the same thing, but the opposite. Instead of having one function dominate the other, we don't want to have either function dominate, and we should be good. So if when you divide the two infinitely large values, the one from the series you know, one from the series you don't, if they have a finite answer, then both of those functions have the same end behavior. So if you were to choose, for example, 1 over n, like the harmonic series, for our comparison series, and you do this limit comparison test and you get a finite answer like 7, or 100, or 1,000,000, something like that, then whatever series you're comparing it to has the same end behavior as the harmonic series, which means harmonic series diverges. They would both diverge. So let's go ahead and try to lay this out. Given two series, and assuming that they have positive terms, let L equal the value of the limit as n goes to infinity of one function divided by the other. And notice that the order is unimportant. So it's a little bit different than the ratio test, and I can understand confusing these two. The ratio test over here says take the n plus first term of a single series and divide it by the nth term, divide two terms one after another, and the order there is important. However, if you do the limit comparison test, the order is not important, because either, let's say that here you get a finite value like 1/2, Well, if you do the opposite, then you're the reciprocal, then you'd get 2 over 1. Both of those are finite values, so it would tell us the same conclusion. Doesn't matter the order here, which is very nice. If the value of L, the value of the limit when you divide one series by the other, one infinitely large term of a sequence by the other, then the two overall series share the same end behavior. They both diverge or both converge. However, if you get an answer of 0 and the series in the denominator converges, then the series in the numerator also converges. However, if the opposite is not true. So if L equals 0 and the numerator converges, then you don't know much about the denominator. And then last but not least, if the limit equals infinity and the series in the denominator diverges, then the series in the numerator also diverges. This is directly related to the direct comparison test, right? In the direct comparison test, we had 4 options where 2 options were inconclusive and the other 2 options told us an answer. That's kind of like what's going on here. However, good news for you, items 2 and 3 are beyond the scope of AP Calculus BC. You do not need to know those. So if you're asked to do the limit comparison test, it's going to be this one. It's going to be, you're going to get a limit from 0 to infinity. It's going to be a finite number. So let's run through 2 quick examples then. First one, we have to determine whether the following series converges or diverges. Step 1 is always deciding on a comparison series. What do we want to compare the series above to? Now, if you were doing a direct comparison, you'd really probably want to ignore, you'd want to make this as simplistic as possible. And you say, what about 5n to the 4th over 2n to the 6th? And we choose that because if you have 5n to the 4th over 2n to the 6th, you can simplify this, and that becomes 5 divided by 2n squared. And if you think of this, it's 5 halves times 1 over n squared. That's a p series. N is greater than 1. That guy's going to converge. That seems like a good one to compare. And then you'd actually have to write out all the terms of this and compare it to this guy over here, and then compare some fractions. Things get crazy. It's no fun. Well, good news for you. For the limit comparison test, all you really need to do is figure out what will this simplify to if we ignore all the non-dominant terms and ignore the coefficients. So essentially, we're just looking at what is n to the 4th divided by n to the 6th. And we hope that when we simplify, we know the convergence or divergence of the series, and we do. 1 over n squared, p series, we know that converges. So let's go ahead, since we know the n behavior of 1 over n squared, we're going to compare that to the original series. How do we do it? Well, limit comparison test. We take the limit as n approaches infinity of one series divided by the other. I usually take the more complicated series and put it in the numerator. You don't have to, not a big deal. Something like this, divided by the original denominator. Cool, and then all of this is divided by my comparison series, like so. We do not need absolute value here, but you can do it if you want. We're going to positive infinity, so either way, and let's go ahead and work it all out. We've done something like this before with our ratio test, so it shouldn't shock you when I flip or take the reciprocal of the denominating fraction. Something like this, so times n squared over 1. And then notice what we're doing by choosing this n squared is we're really going to make the 2 powers the same in the numerator and the denominator, and it should make our lives a little bit easier. So the limit as n approaches infinity. The numerator becomes 5. We're going to add 2 to every power here, something like this, and something like this, divided by, and then the denominator is not changing. Now taking the limit as we go to infinity here should be really easy. Strip away the less dominant terms here, so it becomes 5n to the 6th over 2n to the 6th. Factor out the 5 halves, irrelevant for the point of this limit. And hopefully we see that this all goes to 1. And so the value of my limit is 5 halves. Is 5 halves a finite number between 0 and infinity? Yes. It is. And because it is, then that means that my 2 series share the same end behaviors. Whatever this guy does as well. What does this one do? Well, this one converges. And because this one is a p series that converges, so does the other. We should write a sentence as a conclusion here. I just ran out of room. So if you wanted to write the sentence, or if you have room, it'd be something like this. As the series 1 over n squared is a p series with p greater than 1, it converges. Due to the limit comparison test, the original series also converges. Nothing terrible, very quick. I imagine you could probably compress it into here to here to here if you wanted to be most efficient. Not a ton of work, nothing bad at all. Okay. Let's go ahead and try one more. So 1 over 3 to the n minus n. I always like to strip out the least dominant term. That's going to be my negative n over here. So we are going to go ahead and compare this to the series from 0 to infinity of 1 over 3 to the n, which, just as a friendly reminder, since we will need this later, I'll actually write a conclusion this time as 1/3 to the n. That's a geometric series with r less than 1, so we know that converges as well. Okay, limit time. We are going to find the limit as n approaches infinity. 1 divided by 3 to the n minus n divided by 1/3. Let's keep it the same. 1 over 3 to the n. And I mentioned you don't need the absolute value. The reason you don't need the absolute value here is one of the necessary criteria for the limit comparison test is both series are positive. So if they're both positive, why use absolute value? Okay, we continue through. The limit as n approaches infinity. We'll do all this in 1. This becomes 3 to the n divided by 3 to the n minus n. We use our dominance here at infinity. Exponentials are way more dominant than n, which is just a boring linear function, and so we end up with 1. As we got a value between 0 and infinity, both series share the same end behavior. So we should probably actually write a sentence this time. As the sum from n equals 0 to infinity, 1 over 3 to the n is geometric, with r equal 1/3, which is less than 1, the series converges. So we talked about why 1 over 3 to the n converges, but we need to relate this back to the original problem, as the limit comparison test returned a result of 1, then the sum from 0 to infinity of 1 divided by 3 to the n minus n also converges. Easy enough. And we're good. The last page of your notes for today is really just a nice summary of all the tests we've done so far. I like to do this every other day or so, just so we keep them all fresh. At the end of this, you are going to get a nice, we'll call it a formula sheet. It's really a series sheet to try and keep all these straight, because there are a ton of them. I will tell you that you probably find yourself using the ratio test, the limit comparison test, and then the alternating series test that we'll learn next class more than any of the others. Most of this has been foundation, and although you should know the others and you need to keep practicing them, those are probably the most important. So here we go. This is going to be a nice run-through of when and how to use each of these. So what do? Well, the first thing we want to do is we always begin with the nth term for divergence test. I probably could have shortened that. Probably could have just said the divergence test. And that's where you take the limit as n goes to infinity, and if the limit is not 0, then you can stop immediately because your series diverges, right? That's where we want to find the limit as n approaches infinity of the actual sequence formula, and that better equals 0, right? If the individual terms of your sequence don't go to 0, then when you add all the terms of the sequence up, it won't be infinitely large. Next up, is your series one of 3 special series we should recognize immediately? And are you able to find the sum? Well, the first one is, of course, the one we just talked about. That's our geometric series. Okay. As long as the absolute value of r is less than 1, the series converges. And to find the sum of a geometric series, we apply the formula. The infinite sum equals the first term, right? Remember that, divided by 1 minus r. Not sure why there's a big gap there. The second one is a telescoping series, and this one is outside the scope of the AP exam. It doesn't appear there, but it appears pretty much everywhere else. I'm always surprised the AP exam doesn't have it, so it's worth remembering. You see these in 2 different ways. Either you see them as 2 rational functions subtracting, right? Such as, well, what would be a nice example of that? It might be something like, and you're going to have to write small here, the sum from 1 to infinity, maybe we'll start at like 3 or something, of 1 over n minus 1 minus 1 over n minus 2, something like that. Or as a single fraction, so those 2 fractions put together, where you need to use your partial fraction decomposition. decomposition to find the sum. Right? Now, to actually find the sum, you list out the terms until they start to cancel out. Right? You should see a pattern pretty darn quickly. And then don't forget to list out the same number of terms at the end of the series. Those will still have n in them because they're infinitely large. And then you take the limit as n goes to infinity. The last special format of a series we should recognize quickly is a p-series, right? Those are in the form of 1 over n to the p power. And, of course, these series diverge when p is less than or equal to 1 and converge when p is greater than 1. Now, we can only use the p-series as justification if there's only one term in the denominator and nothing in the numerator. You can play with it a little bit. For example, if you were asked for, the justification of 3 over n cubed, then you could certainly rewrite that as 3 sum from 0 to infinity of 1 over n cubed and talk about that this is a p-series. However, if it's something like this, where it's n equals 1 to infinity, it's 1 over n cubed plus 1, you're out of luck for the p-series. Even though you're like, but though adding the 1 isn't going to change anything. In fact, it'll make it converge faster. You're right. You still need a test, though. And in that case, if you want to strip some terms away to find the answer, then I almost always suggest the limit comparison test. The limit comparison test, you would compare this to 1 over n cubed. And if you do it in your head, you're going to end up with n cubed over n cubed. That's 1. They share the same behavior, and therefore it converges. So just be careful about that. Now, if you're able to integrate your sequence, then you want to try the integral test. Now, just a friendly reminder about the integral test, there are a couple things we need to remember. First, your series better be, or when you turn it into a function, it better be continuous, positive, and decreasing. It has to be all three of those, at least over your interval you're interested in. And the second thing is the integral test doesn't actually give the sum of the series, right? The answer to the integral is not the answer to the sum. You can bound it, and I think we learned before something like if you go from a to infinity of your series, let's call it f of n, right? That is going to be slightly smaller than the actual value of the series, a sub n, which in turn is going to be smaller than the first term plus the integral of the function. So we should keep that in mind, but that's really about as far as we need to go. Now, if you're dealing with a sequence, right, our general term of our sequence involving n factorial a sub n, I would really suggest the ratio test. Okay, the ratio test is, of course, the one where we do the limit as n approaches infinity of the next term divided by the current term, and if we get an answer that is less than 1, then we know that our series converges. And the reason we're doing that is this is like a geometric series. When we got infinitely far, it turns out that a series we use the ratio test on behave just like a geometric series, which means there needs to be an actual common ratio between the two. And we know that common ratios for geometric series have to be less than 1 in order for the series to converge. If we have sequences of rational polynomials, so what does that look like? Like ax to the n plus bx to the n minus 1, right? Over something like, I don't know, let's do cx to the n plus dx to the n minus 1, and so on and so forth, right? So essentially x cubed minus x to the fourth, or whatever. Then I would really suggest here we do the limit comparison test. Or if you're feeling very bold, you can do the direct comparison test. I always suggest comparing the function to a p-series or something geometric, and we did 2 examples on that today. Now, these are really just guidelines. You do not have to go in this order. You do not have to memorize this. You do need to be comfortable with all of these tests, though. So your bookwork for today actually takes you through the limit comparison test at the beginning, and then at the end, if I remember correctly, you really get some chances to actually try and decide which test you want to use. So thanks for hanging in there. We only have 2 more days of this left, and then we actually get to why we're learning all of this, and it is super cool, I promise.